Power factor charges are being added to irrigation rate schedules across Nebraska in 2022, and your utility might be one of them. And if it's not in 2022, it might be in future years. So this presentation is going to talk about how to reduce or even avoid those charges. First of all, let's chat about how you are charged for electricity. You are charged usually a customer charge or a base fee every month, a per kilowatt hour energy charge, a demand charge based on your peak use, and then transmission and distribution charges and some other charges and fees. Transmission and distribution charges are generally in Nebraska, I see them kind of integrated into the energy charge, so they're not on an electric bill, but they are trying to recover enough dollars to cover the transmission and distribution infrastructure. Today we're going to talk about power factor, which is an adjustment to the demand. So they're going to increase the demand in order to cover poor power factor. Poor power factor is caused by inductive motors. This is electric motors, transformers, and high-intensity discharge lighting. So in this case for irrigation, it's those big electric motors that we're talking about. Power factor is a measure of how effectively the equipment converts that power into useful power output. This is my representation of an irrigation motor where the electric utility is providing you electricity to run that motor. Part of that electricity is working power, power that goes directly to converting turning the motor and thus pumping water. Yet some of that electricity is non-working power, which goes to just energize the electric motor itself, energize those coils, and keep it functioning properly. And thus the utility has to provide you with total power, and yet your electric bill only represents working power. And that's the adjustment that we're talking about. So the utility has to have a supply system that electric generators and electric transmission grid large enough to provide you both active power, which is the working power, and reactive power, the non-working power. And right now you're only being charged for active power. So this is that adjustment to do that. Now, what they'd really like to have happen is that you reduce that reactive power, thus they don't have to provide it, and thus you have a savings, and then they're able to burn less coal, have more capacity on their electric grid. Let's look at power factor in a different way. If we were trying to have enough power to move this cart along a track in the direction to the right, we could hitch a horse to it, and a horse could pull that in the direction to the right. And that would be the amount of work that horse would do would be the working power, active or real power. The trouble is the horse can't walk on the tracks, so the horse has to be offset off of the track and pull both in a direction to the right and a direction down, and so there is non-working power that horse has to do, power that doesn't do any good, doesn't do any movement to that cart. So that horse has to provide total power. So when we feed that horse or buy the horse to do this job, we have to have a larger horse potentially, and we have to feed that horse more to do that total power, even though working power is what we want, the movement of that cart in the direction to the right. So the power factor is the ratio of working power and total power. So if we were to throw some numbers out on this example, if working power was 100 kW and total power was 120 kilovolts apparent, in this case, we would have a power factor of 0.83. So what if we could move that horse closer to the track? That's the goal, would be to reduce that non-working power. In that case, the working power was still 100, the total power turned into 106, and the power factor improved to 0.94. So that's really what the utility is trying to influence you to do, is either reduce that power factor, that non-working power, or pay for the total power. And so that's really what's going on here. In electrical terms, we can think about it from a current and voltage standpoint, because there is a draw of current into that electric motor to energize those coils. It causes a lag between the current and voltage, and that lag is the waste. So the goal would be to minimize that lag. To improve the power factor, a capacitor bank can be put in. A capacitor bank is an energy storage device. that stores electricity, and then those capacitors store those kilovars reactive and release it opposing the reactive energy, and thus minimizing that lag. So if we look at a system with and without power factor correction, or with or without those capacitors, the bottom one with those capacitors, we've minimized that lag, thus we've improved our power factor. To look at it from the standpoint of this diagram, by adding that power factor correction capacitor, which some of you may already have, it's a matter of now looking to make sure that they're working properly, we are minimizing that non-working power, thus less total power has to be provided to that irrigation system. So why are utilities adding this charge now? Well, forever they have been required to have good power factor by the people they buy electricity from. So because they have to maintain a power factor, they are saying now that we can more clearly put these charges in place, we're passing those fees that we've already had for ourselves on to you. Another thing is it's more effective to improve power factor at the source of the poor power factor than on their system. So they're trying to, again, have this system work more efficiently across the whole board. They don't want to have to oversize their system for the poor power factor. Also, by having better power factor, they have more capacity in the system. The last thing is these advanced electricity meters. You'll know that the new electric meters that you see don't have that old disc anymore. They're computer devices, digital devices. Now they can measure power factor in real time. Thus, they can now pass those charges on to you, which wasn't possible before. When we have correction at the source, in this case at the electrical motor, at the irrigation system, it can be a positive thing all the way through the system, from the distribution system, the local power lines, all the way through to the substations, and all the way to the generation, where we have to then burn less coal, less natural gas, etc. So it can be a help all the way through the system. Here's my example for some economics to show you on improving or not on power factor. I'm using a 2-day load control schedule from a utility. Your load control schedule is going to be similar, but maybe slightly different with the numbers. So you simply have to translate this into your rate schedule. So for this rate schedule, they're charging $41.75 per horsepower. Yours might charge for horsepower or kW, but just put in the value there for what you charge per horsepower. That's the demand. Then you look at your bill. What was your peak horsepower during the billing period, or your peak kW? In this case, 67.94 was the peak horsepower during the billing period. So the demand charge during this particular billing period, which was a growing season, an irrigation season, was $2,836. Now for the power factor adjustment. To calculate this, take the horsepower from the grid or the kW from the bill, 67.94, multiply it times the power factor that is desired by the utility. For a couple utilities I've seen, it's 0.93. I saw one that was 0.90. So you multiply times the desired power factor and divide by the power factor, again, from the bill, the actual power factor that was recorded during that billing period. In this case, 0.829. By doing this math, we get 76, and so we're adjusting the billing demand from 67 horsepower to 76, thus our bill goes up. So 4175 times 76.21 horsepower is 3,182. So with the power factor adjustment, it's $345 more per year. Now, if you have a power factor below the 0.93, you're going to have this adjustment and you're going to have this added cost. If you have a capacitor in place and your power factor is above 0.93, this charge is already zero. So then it's just a matter of making sure that it's working. If you so you can look at your power factor. If it's below that minimum number, then you want to look at that. Can you install a capacitor? Can you improve your capacitor sizing? Can you potentially make sure that it's working? So install a capacitor if you don't have one. Work with your electrician to size it. I've been told by an electrician the cost of these systems can be, $400 to $600. If you think about that, if you're saving $200 to $500 a year, the paybacks are really short on this, so worth doing. Monitor that electric meter to make sure that that capacitor is working. This is going to be a challenge. It's going to be difficult to catch a broken capacitor until potentially it's too late. So you want to be watching that. I think you really probably could only need to really pay attention to this maybe once a year, probably in the first week or two of irrigation season, to make sure that that capacity factor is as close to the minimum as it can get, or better. So if you can get it better, that's great. So then maintain if you need to. If you recognize that your power factor is low because your capacitor failed and looks like you're going to get a charge, yet you still want to get this fixed, call and talk to your utility about it. They may be able to reset. They may be willing to do some things to try to make it right, because you're doing what you can to improve that power factor. If you have any questions, great place to call is your utility. Talk to them, communicate with them about what you're trying to do. And then if you have any questions for me as well, give me a call.